Yeah, so today's lecture is on rigid body motion. Just a reminder, key points from last lecture, we talked about integrating the pressure force on a surface. The equation I gave there is a double integral, an area integral of the infinitesimal pressure force at a small differential element on our surface. This equation applies generally. It's not just for hydrostatics, but in hydrostatics, we're able to actually compute that P in this equation. So that's why we first looked at this equation within the context of hydrostatics. But it will come up a lot. So this is just the pressure force. There are other forces in fluid mechanics, but the pressure force is a very important one when it comes to forces that fluids actually create on things. The more general case is you need to use numerical integration for this, but as you did in the tutorial yesterday, and as you'll do on the exams, we're going to integrate by hand just to demonstrate you know how to set up the integral and that sort of thing. Context of today's lecture is our last lecture related to hydrostatics. So the lecture at 12:30 today will be on surface tension. So I'm sure you're as happy as I am to finally be moving on from hydrostatics. So we're actually going to get into some, in my opinion, more interesting elements of fluid mechanics, but hydrostatics is quite useful. And indeed, there's a lot of cases where hydrostatics are something mechanical engineers need to understand and compute forces on structures and things that go underwater and things like that. So the learning objectives for today are to define what a fluid undergoing rigid body motion actually is to compute the pressure, field, and isobars in a fluid undergoing uniform acceleration. We're going to compute the isobars in a fluid undergoing uniform rotation. And we're going to compare and contrast between hydrostatics, what we were doing before, and rigid body motion. There's a lot of parallels that we can draw between these two cases of fluid motion. Okay, so rigid body motion. I'm going to go back to our F equals ma for a fluid for a second. So you remember the forces were pressure, friction, gravity, and surface tension. Before in hydrostatics, we said A equals 0. So that means summation of forces is 0. We're going to make a slight modification to this. So we're going to still assume no relative motion of fluid parcels. That leads us to be able to neglect friction forces. So we're going to neglect friction, we're going to keep pressure and gravity, and we're going to neglect surface tension. We're going to leave A. So we're going to allow the fluid to accelerate uniformly without motion in between fluid parcels. So that means our fluid kind of behaves as one rigid body in acceleration. So F equals ma becomes this. So this is the pressure force plus the gravity force is ma. So just a reminder, this is pressure, gravity. Rho dV is the mass of a fluid parcel. So rho dV is m. So the dV's will cancel, and we're left with this. So the pressure gradient is equal to rho G minus A. So you can compare this with hydrostatics without acceleration. So before we got gradient of pressure is just equal to rho G. So now if we accelerate a fluid uniformly, we see that the pressure gradient is really the difference between the gravity vector and the acceleration vector under which we're accelerating that fluid. So maybe you guys can help me brainstorm. So can anyone think of some examples of of this? So where a fluid might not move relative to the parcels might not move relative to each other, but that whole fluid as a bulk undergoes some sort of acceleration. Any examples? Yes, please. Yeah, yeah, exactly. That's a good example. So you have like cement, and as the truck accelerates, the cement will kind of move. If you assume the acceleration is small enough so that it doesn't induce like a lot of flow, that will move kind of as a rigid body. So it's the same thing if you have like a cup of water in your car, for example, and you start accelerating, you'll notice, like in that original lecture slide picture I had here, the surface of the water now makes an inclined angle relative to when it was stationary, it's just a flat surface. So that's one example. Any other examples you guys can think of? So this is yeah, this is not just for like cups of water and tanks. So like fuel tank in a car is a good example. If the acceleration is small enough, the fuel can sort of slosh. So that sloshing could be thought of as the fluid undergoing a rigid body motion. Once the sloshing kind of induces like flow and turbulence and vortices and stuff, that's not rigid body motion anymore. But when the fluid parcels aren't moving relative to each other, which occurs in a lot of cases, that's when a fluid undergoes rigid body motion. Yes, please. Uh, yeah, I mean, pardon me? That's a good question. Yeah, so the fluid in your ear, I'm not really sure how the fluid in your ear works, to be honest. But I am going to talk about a lot of biological effects due to the pressure gradient. Yeah, Kellen. Yeah, exactly. So that's what we're going to talk about. So in space, when you have basically you can think of it like the fluid is in constant free fall, so it's weightless. This means that if G equals A, we actually don't have a pressure gradient in in a fluid, say a ball of fluid floating in outer space. So that's a good example. So that actually leads me to an example that I was going to talk about. So for example, our bodies kind of evolved to deal with a hydrostatic pressure gradient here. So remember I was calculating like the pressure of water in that glass, and there's a decent pressure difference between the top of water in the glass and the bottom of the water in the glass. But our bodies are tall relative to that glass. So your I guess cardiovascular system has adapted to be able to deal with that hydrostatic gradient, which is normally just G downwards. So when you mess with that, like for example, you increase the force of gravity, like if you're in a fighter jet doing a tight turn and you experience harder G, you have a higher hydrostatic pressure gradient that now your body isn't adapted to deal with. The same thing, this is a problem astronauts have in space. So they have to deal with basically no hydrostatic pressure gradient, but your body is used to dealing with basically a higher hydrostatic pressure in your feet and a lower hydrostatic pressure in your head. So there's something, I'll show a picture here. There's something called swollen head syndrome that astronauts have to deal with. So here's an example of an astronaut. I forgot this astronaut's name, but so here's a picture of her on the left when she was on Earth, and then on the right when she was in space. So your face kind of swells because your cardiovascular system is used to having to work harder to get blood into your head relative to your feet. So this is something astronauts have to deal with, and it's actually a big concern for space travel. So there's this study they're doing in France where they're paying people to basically lie down in a bed for 60 days at a certain angle to try and study the effects of the lack of hydrostatic pressure gradient on our bodies in space. So you can't leave the bed for 60 days. The people get paid to do this, but I actually spoke with somebody who was part of this um, study. It's really interesting. You don't really think about the hydrostatic pressure gradient in your body, but this is an interesting article that you can read. So Yeah, so they basically have these people lie down to counteract the hydrostatic pressure gradient that's created by gravity. So yeah, hydrostatic pressure gradients are important. I'm going to do some special cases now of this equation. So I'm going to define this coordinate system here. So x, y, and z. This is a little bit different than the previous coordinate system we're using. So now g is 0, negative g, 0. So g is negative 9.81 because our y vector is pointing up. I'm going to write out the terms of this vector equation that we derived here. So the pressure gradient is rho g minus a. So let's write it out in Cartesian components. So we have partial p by partial x. So the first component is negative rho ax. Partial p by partial y is negative rho g plus ay. Partial p by partial z is negative rho az. So those are the three components of the vector equation up there. I'm going to turn this into a table so we can see some special cases. Let's think of the case where there's no acceleration. So the acceleration is 0. So if we have a fluid at rest with no relative motion between fluid parcels and no acceleration, we know that we should get the same thing we got for hydrostatics, right? Because that's how we derived the hydrostatic equation. So in that case, that first term is equal to 0 because ax is 0. Second term is negative rho g. The bottom term is just 0. So this is hydrostatics. And that's what we just looked at. So a fluid that isn't accelerating. So we got, when we were doing hydrostatics, we got positive rho g just because of how we defined y related to g. Now we get minus rho g, but you'll get the same pressure distribution. As you mentioned, so that case where acceleration is equal to gravity, that's like a fluid in free fall. So maybe you could think of this like the fuel in a tank in a jet that's falling, or yeah, a plane with 0 g, something like that. In that case, you get 0 in all these cases. So there's 0 pressure gradient. So that would be the case of, say, a free fall or weightless fluid. So for a free falling or weightless fluid, like in gravity, there's no pressure gradient because that pressure gradient in hydrostatics is created essentially by the weight of water or weight of fluid above you. So since nothing has any weight, the pressure would be uniform. Let's consider a case here now of uniform linear acceleration. So I'll break it into 2D just to make the drawing a little bit easier. Let's say the acceleration vector of our fluid and rigid body motion is ax, ay, 0. So 0 acceleration in the z direction. We have some acceleration in the x and y direction. So I'll draw this fluid now. So say when that fluid was at rest, it had a free surface like that. Now under acceleration, the free surface looks like this angled line here. So this is like your coffee cup in your, or something like that in your car. As you accelerate, the free surface will be at an angle. And that free surface is indicated with the triangle there. And that angle from the horizon, aka the original free surface angle, will be called theta. Now that free surface is orthogonal to this vector here, which is g minus a. So the gravity vector minus the acceleration vector. And our coordinate system for this problem is defined here. So we're going to call the coordinate system 0, 0, centered at the bottom left of this fluid. This is a little bit different than how we did it in hydrostatics, but they are equivalent. So just for the ease of the math, we define the coordinate system, the point 0, 0 is in the bottom left there, and the y vector is pointing up. So this is probably a more standard Cartesian coordinate system that you've seen. In this case, I won't go through the derivation. So the original equation is pressure gradient is rho g minus a. We get a pressure distribution now of this. So P0 minus rho AX x minus rho G plus AY Okay. So that's the equation for the pressure distribution in this fluid based on the coordinate system. P0 is the pressure at the point 0, 0, which is that bottom left corner of the fluid. So the isobars of this fluid now, we still get that uniform pressure gradient, but the isobars are now angled. So the isobars are like this. And that angle is the same angle as the free surface angle. The angle of that free surface, it actually doesn't depend on any fluid properties. It just depends on the geometrical relationship between your acceleration vector and your gravity vector. So that angle is tan theta is AX over G plus AY. So that gives us the angle that the free surface makes. So the reason for that is if we consider our vector, I mentioned that vector G minus A is quite important because the pressure gradient, if I go back up to this equation here, this equation says one vector is equal to something times another vector. So it's just going to scale the second vector. So one vector, aka the pressure gradient, is equal to just a scalar multiple of the G minus A vector. So that G minus A vector is important too. Yeah, Aaron? Yes, I drew that quite poorly, but these isobars are, the isobars, if I draw them directly on this, would look like this. So parallel to the free surface. And those isobars are orthogonal to our G minus A vector. So that vector is G minus A. The x component of that is AX. So we're assuming we don't have any gravity in our x direction, which we don't, the way we've defined the coordinate system. And this one is G plus. This is kind of the magnitude of this. The angle is, that theta angle is here. So that's how we calculate the angle of our free surface. So we have an equation now in this coordinate system to determine the angle of the free surface made by a uniformly linearly accelerating fluid behaving as a rigid body. So you think that's a very, very specific case, and it is. So I'm going to do an example, but are there any questions about this? The derivation of this is not really something I want to spend that much time on. So I want to ask you to derive this P equals P0, the equation there. Okay, I'm going to do an example just so we get some numbers in. So the example is will the coffee spill in an accelerating car? Say we have some sort of coffee cup. The original free surface of this is a coffee cup here. Just the original free surface is that dashed line here. And we're going to accelerate, say the car is accelerating like this, where AX is 3 meters per second squared. So our new, as we're accelerating, this is a positive x direction accelerating. So we're going to get the free surface of the liquid looks like this. The angle in there is theta. So there's going to be a certain change in height here on the left side. I'll call that delta y. And I'll give you the geometry. So say originally you had this coffee cup is 8 centimeters wide or in diameter. You can think of this as looking down the center plane of this fluid. The original height from the bottom was 6 centimeters, and the overall height of your coffee cup is 9 centimeters. So the condition at spilling will be if you accelerate fast enough that the angle of the free surface goes steep enough that your delta y will be above that 3 centimeters, which is the difference between your original fluid height and the actual edge of your coffee cup. Are there any questions on the problem setup? Question mark there. So this problem is solved purely geometrically based on just the angles, the magnitudes of our different vectors. It actually doesn't depend on the fluid properties at all. So this will be, we solve this problem by just looking at, so let's calculate the angle there, the free surface. Tan theta is AX over G plus AY. In this case, we're saying, just a reminder, our coordinate system is here and here, X and Y. So we're not saying we have, say you're just on a flat road or something, there's no Y acceleration. So you're just accelerating in the X direction. So AY is 0. So tan theta is 3 over 9.81. This gives us an angle of the free surface of 17 degrees. So that delta y max, now we can calculate that. So delta y, we're going to look at this triangle here. So that triangle is kind of half the width of the cup. So delta y is going to be 4 tan theta, which is 1.22 centimeters. So delta y is less than that 3 centimeters. So no, the coffee will not spill. Any questions there? It's just pure geometry with the angle being dictated by the angle made between our different accelerations. So now let's calculate what is the maximum pressure in the cup. So where do you think the maximum pressure in this cup would occur? If the cup wasn't accelerating, say it was a free surface, no acceleration back to hydrostatics, the maximum pressure occurs at the maximum height in the fluid, right? So when we accelerate, where does the maximum pressure occur? Do you have an idea? Exactly. Yeah. So the maximum pressure occurs here, which is the farthest distance of any point from the free surface. So I'm drawing there the line, if you were to draw a line between all the points in the fluid and the free surface, again, these are not isobars, the maximum, the longest line would be here. So at that 0, 0 point. So based on our coordinate system, we have our equation p equals p0 minus rho ax x minus rho g plus ay. This is the equation I gave above for the pressure distribution in this fluid. And a reminder, the P0 is the pressure at 0, 0. So that's actually the pressure at the bottom. So we're gonna use this to calculate the pressure of the free surface, which we know is 0 in gauge units, to get P0. So we're going to calculate at the free surface, which pressure field will be 0 there if we say we're working in gauge. Specifically, we're going to calculate the free surface up this wall. So we're going to calculate the pressure at this point here. Everyone can see that? So the pressure right up the left wall. So that left wall actually has an x coordinate of 0. And again, ay was 0 in this case. The y coordinate of that is positive. We calculated that height. So that's 708 pascals. So just to show you where these numbers come from. So that 0 again, that 0 is the x coordinate in our coordinate system defined here. So if we go straight up to this free surface, we don't have any, we're still along that y-axis. The y coordinate is the 6 centimeters plus the delta y that we calculated. So that's 6 plus 1.22. So this is actually, P0 is the pressure at 0, 0. So P0 is 708 pascals. Any questions? Yep. Yeah, good question. Yeah, so AY is 0. So this is just rho g y. Yeah. The last bit is y. Yeah, that's a good point. It looks like I'm adding the way I've written that, but that's just y. So AY is 0 for this problem, so that's why we just took it out. Any other questions? Yes, please.
Like we're looking at the situation where you have X and you don't have Y, but if you have Y and a fluid moves up in like a bottle, and then you'll have technically like a vacuum at the bottom. Can you get this? Can you calculate that with this, or do you need more information?
So I guess in like a bottle, the maximum pressure is still at the bottom. That's just hydrostatics.
fluid moved.
I guess I'm not sure what you mean by all the fluid moved up.
You hit the bottle and the bottle moves down faster than the water goes. But anyway.
Yeah, I don't know if that's really rigid body motion, then there's probably some other like mechanism happening there. If you know what I mean. Yeah, Ian?
No, just doing Watson's one where it's getting clarification.
Okay. Yeah. Yeah. Where it creates like bubbles and stuff at the bottom, that's a different mechanism. That's not going to be rigid body motion. That probably is what's happening where you hit the bottle and the bubbles happen is something like that. Some sort of negative pressure is created that creates like cavitation in the water. I don't know. That would be my guess, but I don't know. I'm not sure I totally understand what you're talking about, to be honest. Okay. Any other questions? Okay. So that maximum pressure, I calculated it in our coordinate system here. I'm just going to clarify the coordinate systems. So before when we did hydrostatics, we had kind of a flat fluid, the free surface. And now we have a fluid with an angled free surface. The coordinate system we were using before was like this. So we said y was downward and p0 was here. The above equations for the linearly accelerating fluid use the following, use this coordinate system. So p0 is here with x now and y. The interesting part about this linearly accelerating fluid, you can see that second term in this. When we did this equation, we basically just plugged the numbers into the equation I gave in this coordinate system. The second term here, which is the only term that actually ends up mattering, is still just rho gh. So pretend we had like a flat fluid here. The pressure here is still just rho gh. And the pressure there is still, well, yeah, the pressure there would still, well, I guess it would depend on x there. So the pressure along that bottom is just rho gh. So that increases because the height of fluid above it increased. Yes, Aaron. Yep. Exactly, yeah. We say the overall pressure is 0 at the free surface, so we're working in gauge units. That's the actually only known point we have before we start doing the calculations. So the two coordinate systems, they give you exactly equivalent answers. There's no magic going behind here. They're just different coordinate systems you use to define different pressure distributions, but they give you the same pressure at any point because the physics really just they don't depend on the coordinate system. So the physics won't change. It's just the definitions of our x's and y's and p zeros that change. So this is just to clarify the difference between the two coordinate systems here. Okay. We're going to talk now about rotation of a fluid. So let's say we have the same fluid. Say this is fluid in a cup or something. And it has original free surface here. Now, about the center line of this cup, we're going to rotate this at some speed, omega. So say you have like a cup of water on a turntable that's just rotating. So what the fluid does now is it does like this. It creates a parabolic shape. So that rotation kind of pushes fluid outward against the walls, and it's balanced by gravity, and it creates a parabola. So before we were just doing linear motion or linear acceleration, so that just changes the angle of the free surface. But now if we rotate this, we get a parabolic shape. So we're going to do this we're going to define now like a cylindrical coordinate system. So we're going to take R, the coordinate system in red. So our cylindrical coordinate system here is Z, is the height there, and R being the radius. So some fluid parcel here, this is just centripetal acceleration. So some fluid parcel here at a radius r, we know how to relate the acceleration of that fluid parcel to omega. So now our equation of motion, we can write this in cylindrical coordinates as this. So partial p by partial r is rho. I'm writing gr just for clarity. So gr minus ar. But we're still saying g is downward. So there's no gr. So r is like a horizontal coordinate in this case. It's the radial coordinate along this cylinder. So this is kind of like a rotating cylinder. AR we also know is, so rho 0 minus, we know that acceleration is in the negative r direction. Partial p by partial theta 0. So these are r, theta, z, again a cylindrical coordinate system. So this is still just rho g minus a, but in this new coordinate system, which is r, theta, z coordinates. So I'm not going to derive the equation for the isobars because it requires something we haven't seen yet. I'm also not going to really worry about the pressure distribution in this fluid, which can also, you can derive the pressure distribution for this rotating fluid case. But the equation for isobars is interesting. And again, the derivation requires the material derivative, which we're going to talk about I'm sure a couple lectures from now. So derivation requires material. So in this case, we get a parabolic shape. So the z isobar is equal to omega squared over 2g r squared plus some constant c. So c here is a constant. So these isobars are parabolas, and they all have the same parabolic shape. So that parabolic shape doesn't depend on z. Sorry, that parabolic shape is constant, but we just shift that parabolic shape up and down with that constant c to pick different isobars. Just the same way, like when you did streamlines, you had a constant c that varies. So you can just vary that constant to get different isobars. So this means that isobars in a rotating rigid body are parabolas. It's kind of a parabola, like a revolved parabola. Also note that the free surface is actually an isobar. So the free surface of the fluid is an isobar. So the isobar, the first isobar we could get is like that. So you can think of that as like the isobar for P equals 0. So all along that line, P equals 0. We're at the free surface. Then the P is a little higher along this isobar, and so on. And those parabolas are just all the same, and they're just shifted down. It's the same thing in these fluids, so that the free surface is still an isobar here. It's kind of that isobar of P equals 0. So what we can do if we have a fluid and we start rotating it around an axis, the free surface turns into a curved shape. So can anyone think of like a use we would have for a parabolic curved shape? This is a hard question. What if the fluid was reflective? Yeah, we could turn it into a mirror. So if you use a reflective fluid like mercury, you can actually create a mirror out of this revolved fluid, and it has really nice optical properties because you can vary the properties of this mirror just with the rotation speed of your fluid. So this is actually a method they use for, it's not very common, but it has been used for creating telescopes. So there's a liquid mirror telescope. And it rotates at 8.5 RPM. I have a picture of this telescope here. So this is actually done at UBC. So they have a huge disk full of mercury here, which is a toxic fluid, a massive pool of mercury, and it's on this, it just basically rotates at a constant speed, and the surface of that creates a really nice mirror that they can use for astronomical observations. So you can create quite big, stable mirrors using this method, where normally it would be quite difficult to do this with glass or something. Um, so yeah, at UBC, I think this is actually decommissioned now, but for several years they had this massive pool of rotating mercury in some sort of plywood shed out in the mountains. So that's yeah. Um, so there's I think there's other projects to do liquid mirror telescopes like this, but there's some challenges with it. So the number one challenge being it can only point straight up, so you can't actually really aim it. So you're just kind of, there are uses for, they're called zenith telescopes, where they always just point straight up as the Earth rotates. Are there any questions about this? Like, your comments? Yeah.
Brain motion with SORs.
The isobars in that case, I believe they would. So you can't. I think you'd be able to angle the free surface in that case because you would accelerate it and rotate it. But like this thing, I think is already hard enough to get to work. Like if you're just rotating it. So if you put this on the back of like a truck or a plane or something, like it's just going to be impossible to aim practically. I won't ask you to do that on a exam or anything. Like combine these two types of motions. But the optical properties of this, I think, are quite an interesting problem. So, any other questions or comments on this? I posted some articles and stuff on Learn if you're interested to read about the challenges they faced in actually getting a big pool of mercury to rotate at a stable speed. There's a whole bunch of issues they had, but it's an interesting case of how we can use fluid mechanics for astronomy. Okay, so that's all I have. If there's no other questions, I'll see you guys at 12:30. Thanks.